Recall the maxmin problem in normal form. We have a minimization problem in red over variables sigma2 of the expected utility of player 1 once the strategy of player 1 is given. And we have a maximization problem in green over the strategy of player 1 of the result of the value of the minimization problem. Recall that we can represent an extensive form game using the normal form and then finding a maximum strategy. But the normal form is exponentially large in the size of the game tree, and therefore this approach would require exponential time. However, recall that normal form strategies and sequence form strategies are equivalent. Thus, we can formulate the problem using the sequence form as reported in this slide. The objective function is the expected utility of player 1 in sequence form, where we have the utility matrix of player 1, the strategy of player 1, and the strategy of player 2. We have the constraints that the strategies of player 2 is well defined, and finally we have the constraint that the strategy of player 1 is well defined. As we did in the case for the normal form, focus on the minimization problem. Consider the minimization problem as a primal linear problem. Our goal is to derive the dual. We have in this case a vector of dual variables that we call v1. Exactly, we have one scalar variable for each equality constraint. So the cardinality is equal to the number of information set of player 2 plus 1. The meaning of the dual variables v1 is simple. Each v1 is associated with an information set of player 1, and it represents the expected utility of player 1 from that information set to the terminal nodes. Here you have the dual. By strong duality, the primal problem being linear, the primal and dual problems have the same optimal value. The maximization is performed over variables v1 that are, as said before, the dual variables. The objective function is the scalar product of vector f2 and vector v1. Recall that f2 is a vector of zeros except for the first position, in which we have a 1. So this scalar product is equal to the value of the first position of v1. This set of constraints is a bit more involved than the set of constraints we have in the normal form case. Basically, it requires that the value of player 1 at each information set of player 2 is not larger than that one given by playing the action available at that information set to player 2, minimizing the utility of player 1. This term is the expected utility of player 1 given her strategy for every sequence of player 2. This term captures the value of an information set and of the successors. Later, an example is provided to clarify the meaning of these constraints. Come back to the maxmin problem and focus again on the minimization problem. We can substitute the minimization problem with the dual problem, obtaining this problem. Then we can put together the two max operators, obtaining this linear program over the variables r1 and v1. This shows that we can find a maximum strategy in two-player extensive form games in polynomial time in the sides of the game tree. Consider this example. Here the strategy vector of player 1, her utility matrix, and the matrices and vectors of the sequence form constraints are given. Here the general maxmin problem in the sequence form is given. Here the maxmin problem for this specific game is given. We analyze the program in detail. The objective function is equal to the value of v1 in the fictitious information set. This is because the vector f2 is a vector of zeros except for the first position, corresponding to the fictitious information set, in which there is a 1. Here the set of constraints due to the dual of the minimization problem. Start from the last constraint. This constraint forces that the expected utility for player 1 at information set 2.1 cannot be strictly larger than the utility given by choosing action R1 of player 2 at information set 2.1. Notice that if player 2 chooses action R1, player 1 gains 2 multiplied by the probability to play R1 L3 plus 4 multiplied by the probability to play R1 R3. This constraint forces that the expected utility for player 1 at information set 2.1 cannot be strictly larger than the utility given by choosing L1 of player 2 at information set 2.1. Notice that if player 2 chooses action L1, player 1 gains 6 multiplied by the probability to play R1 L2 plus 9 multiplied by the probability to play R1 R2. This constraint forces that the expected utility for player 1 at the fictitious information set cannot be strictly larger than the utility given by 4 multiplied by the probability to play L1 plus the value player 1 receives from information set 2.1 on. Here we have the standard constraints of the sequence form. These constraints force the realization plan of player 1 to be non-negative.